Hello everyone, welcome back to my channel. Today I am going to explain a new paper called Neural Language Modeling with Implicit Cache Pointers. This paper is by Lee, Daniel Povey and Sanjeev Khudanpur, and this paper is in collaboration between JHU CLSP Lab and Xiaomi Research. And many people may be knowing about Daniel Povey and Sanjeev Khudanpur if you are using Kaldi. And in this tutorial I will explain the overview of the paper. Then I will explain the proposed model or proposed algorithm, which is the implicit cache pointers for neural language modeling. Then we'll see the experimental setup and data sets. Finally, we'll see some results. So many people will be knowing about what is language modeling is. So language modeling, you can simply think of it as what is, if you ask what is the probability of sequence of words x1 x2 and so on, and that is language modeling, or sometimes it is also called predicting the next word given previous words, right? So that is a simple way of thinking, but it's more detailed than that. Like what is, if you can ask a question like what is the probability of I am going to school, right? And obviously the probability of that will be higher if your probability of that will be higher. But if you say what is the probability of going school I am, something like that, like jumbled words, the probability of it will be less, right? So that is language modeling. And in this paper they use something called pointer cache method to capture long range dependency, one thing. Second thing, also to capture the reoccurrence of particular words, right? And this is very much useful in case of speech recognition, where let's say you have a audio recording of 30 minutes, and many cases whatever word the model predicts might repeat in the future, right? Or whatever word we see in the future might have repeated in the past, right? So these kind of things happen, and this is one of the very important thing also in speech recognition. Many people are trying to solve that, and that is called reoccurrence of a word. And in this paper, the idea of this paper is actually based on that kind of scenarios, keeping in mind that some of the words might reoccur in the future, and how do we capture that information and we propagate that information to the future, so that we are able to increase the performance of a speech recognition model. And that is the whole idea, and this is the very interesting thing as well. And so as I said, so predicting the rare words from long context, right? And they use this memory augmentation idea or memory augmentation unit, which is embedded into a neural network to learn words which are likely to reoccur or likely to repeat, right? So, and we will understand how that works in the coming slides. And coming to the results, they have evaluated the perplexity, which is a standard um, uh, metric which is used to evaluate the language modeling performances on different data sets. And in this paper they use this Pentree Bank and Wikitext2 data sets to evaluate the perplexity, so that they can compare the model performance or compare this paper's idea with other ideas which are existing out there, right? And also they show this idea or this language modeling idea is going to improve the performance of a speech recognition model, because speech recognition model also uses language modeling. If you see, it has acoustic model and language model, and language model also plays a very important role in getting getting a very good performance of the whole speech recognition pipeline. And in this proposed approach section, we are going to explain it in 3 different parts. First, I am going to show you the overall idea of the paper or overall idea of the model. Then we will understand these 2 components separately, because even in the paper they are written in separate sections. It will be easy if you can go through these sections separately, so that we get a very good understanding of the whole paper. And sorry for the bad resolution of the image, but So the idea is like this: assume you have a recurrent neural network, and when I say recurrent neural network, you might have seen this kind of image where there are ht minus 2, ht minus 1, and ht. So these are the hidden vectors at time step t minus 2, t minus 1, and t, right? And these are the things as you can see here. So here instead of t minus 2 they are representing as t l minus 1, because they are assuming they have l context or L time steps. So L is basically could be 50 or 100 depending on how many words you want to put a context on, right? So let's say you have HT, or let's come here. Let's say you have HT, which is the hidden state activity at particular time step T. T could be 1 to let's say 1000 if you have 1000 words, and let's say you are at T maybe 100, and the output is going to be, so usually when you have a recurrent neural network, it's going to be like this, right? You have xt, xt minus 2 here, xt minus 1, and xt, right? So usually you will give an input which is xt at a particular time step, and also you will take the previous hidden state activity which is ht minus 1, and you get ht, which is the current time steps hidden activity, and using this you can predict the next word, which could be how do you predict the next word? You just pass this ht, which is hidden vector, through a softmax which is of dimension v, capital V, right? So this capital V is the length of the vocabulary. Like for example, in your data set, if you have let's say 400,000 words, your hidden state, your vocabulary or V could be 400,000. I mean, it's true that you can't put a softmax of 400,000 because it's likely to. There are many problems. You can use many other. There are different ways of solving this problem. But other than that, the simple idea is you take the HT and put it through a softmax, which will likely have a matrix W to transform the, let's say, 100 dimensional hidden activity to 400,000 dimensional probability vector, and then you can choose the argmax of this particular vector and then find the next word, right? As simple as that. That is a standard way of doing language modeling, and that was already this is already published in many papers. If you go back to 2003 Yoshabinji's paper, he says this. Also, if you see the breakthrough word embedding model, they also talk about this. But what is new is in this paper, they not only predict, they not only use this V vocabulary, v words vocabulary, but they also add this component PT, which is of length L or dimension L, right? So what I am trying to say is, when you project this HT, you not only project it to V dimension, but you project it to V plus L dimension. This L is basically the length of the context. Basically, L could be 100 or 200 if you are trying to focus on previous 200 words, right? L could be 200, and this PT at particular time step T is basically L dimension, and the same way you have it for all the other dimensions as well. So the idea is this will likely capture the information about the previous words, which can be used or which can be predicted at the present or current time steps, right? And that is the idea of this P. And why they call it P is because it's a kind of a pointer, because it is trying to look for the previous L capital L number of words, right? So that's why it's called P or pointer, right? So that is the pointer vector, and there is also one vector or one hidden value called mt. So this mt is basically dimension 1. Basically, it is a single neuron which will help us in capturing the reoccurrence of a word. That's why it's called M, because it's a memory. So it's called memory component. We will discuss about all the equations and everything in the coming slide. But the whole idea is you have this MT, which is the memory component, which will help us in to use the reoccurrence or reoccurrence of a particular words, and which can be which we can use it to predict at the current time step. Let's say, for example, you have predicted some word called let's say Xiaomi or Samsung, which which occurred and we have predicted at, let's say, 100 time step, but when we come to 500 time step, there is very high chance that that person might have spoken Samsung instead of Simpson, right? So you can use this memory component to predict that, because usually speech recognition makes mistakes at these kind of similar, phonetically similar words. Like for example, Samson is a word. Let me write it. Sun is a word, and Samsung is also a word, right? And Samsung is a phone. Let's say somebody is talking over the phone about some new brand Samsung has released, and the speech recognition model has predicted as Samsung, but we know that Samsung is a very unlikely word because the context is Samsung, because previously the same person spoke about Samsung, but the assumption is we are going to it's highly likely that the person would have spoken Samsung instead of Samsung. So that's why we want to retain this. So and this memory component, or this MT, will help us in capturing that. And concatenation of the previous L these kind of units, you can form a vector, and we will see how how that can be used to add it to the training pipeline, right? And this is the whole idea of the paper. Hope you guys understood. Let's go in detail about the pointer component. So the pointer component is basically the PT vector you saw, which is of dimension L, right? So so I mean, you have, let's say you have a RNN language model. Let's just assume a simple RNN language model, no need of LSTM or any other fancy GRU or anything. Just assume RNN LSTM, and you get HT at time step T, which is the hidden state activity at time step T. What you are going to do is you are going to project this using a W matrix with some bias to get YT, which is basically the probability distribution of all the possible words in the vocabulary, right? And this YT will be of dimension capital V, and this V could be 100,000, right? If your vocabulary size is 100,000, and you choose the one which is highly likely, right? And that's simple as that. And W could be, W is V cross H matrix, and B is basically the bias. It could be a simple one vector which is of dimension V, right? As simple as that. This is like a fancy, and this is nothing fancy. This is like a very old thing, right? Like 1990s LSTM algorithm, or even older than that, RNN model. But what is fancy is this one. So here what we are doing is we are not only projecting this HT to YT, but we also add this component. So what I am going to do is I take the same HT, I am going to put it through another affine transformation, which is of, which has this sorry about that, you have this affine transformation of dimension of a matrix WP, and I'm going to multiply that matrix by this vector. Then I'm going to get this vector PT, which is of dimension L, right? So I mean, very simple, right? You just project it through W here, and I'm going to do the same thing. I'm taking this HT and again projecting through some WP and getting a new vector PT, but this time this PT is a L dimension vector. Then what I'm going to do is I'm going to concatenate this output, which is let's just call it as ZT, which is basically W times HT plus B, comma this one, which is WP times HT. This does not have bias, right? You just concatenate the affine transformation with WP and W, right? So then you get a huge vector which is of dimension V plus L. Then you apply a softmax through it. So softmax basically gives you the distribution, and then you get your YT, right? As simple as that, right? That is all described in this paper. I mean, this is a simple thing, right? I mean, not that complicated, right? So you got this is a very simple component. This will help us. So what is the advantage of this? Because you are using this pointer vectors, these pointer vectors actually capture the information of previous L words, and we can use those information to predict the current time steps word, right? Current time steps predictions. That's a very good thing. Next thing is the memory augmented pointer component, which is basically basically to capture the reoccurrence of words, right? So what I'm going to do is very simple. You take all you consider the you consider L previous time steps, right? Let's say you are at time step 100, and if your L is 50, you take from 50 to 100, right? And you take all the hidden values of these hidden values, because they are not vectors, because they are like single single hidden neuron at every time step. So you take all the m's, m50 to m100, which is basically a vector. It becomes a vector because you are taking a sequence of single scalars, and that becomes a vector. That let's call it as empty. Then you simply add the pt, which is also of dimension L, with empty element wise, right? So the simple way is you take pt, which is a vector, right, of dimension 1 cross L, and you add to this 1 cross L dimension empty, right? As simple as that, because they are like vector to vector. You just add them element by element, then you get a new vector, and then you use that to predict the softmax, or use that to predict the next word using the softmax. As simple as that. Hope you guys understood. I mean, it's not as complicated as I mean, it's not complicated, it's a very simple thing. I hope you guys understood. Now let's go to the experiment section. So in this I'll just show you the data set. They use two data sets for language model evaluation, basically to compute the perplexity and to compare with other methods. The PTB is basically Pentry Bank data, Wikitext2 is another data set, and these are the statistics of the data set. And for speech recognition, they have switchboard with Fisher transcripts and also WSJ. And as I said, they use PyTorch for PyTorch for training all the model with stochastic gradient descent, right? Let's go to the result section. In result section, there are multiple tables I want to show you. So first, first thing, they have two different LSTMs models to evaluate. First is plain LSTM, as simple like the old Schmidhuber's Shepard-Writers and Schmidhuber's paper, 1997 paper, old classic one. Simple. You just take it and you apply the memory augmentation with the cache idea, which we explained in the previous slides, and you get the best performance, which is in terms of perplexity, right? And also in terms of parameters, you are getting less parameters compared to the PSMM method, which is basically 2017 paper by Richard Sacher and his team from Salesforce. This is the paper name, you can see, and also one paper by this is the paper, and there is another paper called Neural Cache, again 2017 paper published in ICLR, I think, and that's the other comparison. As you can see, LSTM plus Neural Cache with 50 time steps. And as you can see, this paper gets the best performance both on Pentry Bank and on Wikitext2, right? And this is in terms of perplexity. Now they have done the same experiment with something called frag attention based LSTM models. So frag basically frequency agnostic word representation. This is again 2018 paper, I guess. You can check it out. If you go to the paper, it's in reference section 23. And if they use that frag LSTM setup instead of plain LSTM setup, they get even better performance. As you can see, from 67 to they are getting 53, which is a huge improvement, I guess, right? And again, they are evaluating the perplexity on Pentry Bank and Wikitext2 with the different lengths or different context context lengths, 50, 100, and if they add neural cache along with the proposed approach, the memory augmentation, they get even better performance, which is a good thing, right? Now to see perplexity on switchboard, which is a speech recognition data set, they have again tested it on multiple models. LSTM is a plain LSTM, which gets a very bad perplexity, and PSMM, if they add neural cache to LSTM, they get about 44, which is good, but looks like the proposed approach is not as good as the neural cache paper. I mean, usually this happens, like many papers people write, like sometimes these experiments vary, but that's okay, I guess. And if you use transformers with proposed approach, um, again, it's not improving, but still the LSTM plus neural cache is only better. But this is just an experiment with transformer. And also the paper, they claim they were not able to run experiments on GPT, GPT-3 and all these latest huge language models, because they are like industrial level language model, because as you know, GPT models are huge. So they are just sticking with this transformer models. It's okay. So coming to the final result section, which has results for WARs, when they use these kind of cache-based memory augmented models for language modeling, as you can see, the proposed approach only gets the best WAR. Not huge change in terms of WARs. I mean, as you can see, even plain LSTM will give you about same, like 0.1% difference in the ASR performance, which is WR, but that is still fine, right? And that's all for this tutorial. Thank you so much for watching this tutorial. If you are not subscribed to my channel, please subscribe for more of these kind of contents. Thank you.